All right. Good afternoon, everyone. I'm glad to see so many faces and interested persons around this topic. I'm really happy to talk about a topic that was becoming more and more important to us in the last years, and that's basically lifting the greatness of EMF, the Eclipse Modeling Framework, into the cloud with EMF Cloud. I know a flashy title, but more about what's behind that in a second. My name is Philip. I work with Eclipse Source in the office in Vienna. I also would like to introduce my colleague Martin over here, who helped actually a lot to prepare these slides and also the demos. So I'm pretty sure more or less all of you would agree that the Eclipse Modeling Framework and all the technologies that exist around the Eclipse Modeling Framework are awesome, because based on that we can build very, very efficiently very nice modeling tools ranging from form-based, table-based, textual, diagram-based modeling tools that can be combined arbitrarily however you like with each other. So that's really something that has been helping us a lot in the last years. However, more and more at the same time, there is a requirement growing more and more that we also would like to have those tools be available in a cloud-based application. That means instead of the Eclipse Rich Client platform, we very often and very happily use Eclipse Thea, which is basically a replacement for an application platform, building applications. And luckily there are more and more cool technologies that have emerged in the last months and years, ranging from JSON forms, language server protocols and language server implementations, as well as graphical language servers for diagram-based editors that we can use to build such cloud-based modeling tools. However, as I mentioned before, we really liked and we really do like the Eclipse modeling projects and the technologies within this project. So what we actually want to do is to reuse as much as possible of this huge functionality, of huge bandwidth of functionalities that is available in those technologies. And actually we can do that if we can do that for most parts if we put them on the server and reuse the functionality there. So we've been building a couple of applications with our partners in the last year for cloud-based modeling tools. And during that time, we were quite successful with this approach. However, at the same time, we realized that there is more and more application-specific custom code growing up that we were using to basically hook up and bundle together from communication up to management from these client-based technologies to hook them up to using EMF on the server. And we looked at those application-specific parts and we were thinking, okay, we could actually extract a generic part out of that so that we could use the same component maybe in other applications as well to help us getting more and more efficient, because that's actually what the Eclipse Modeling Framework and all these projects were so, I would say, outstanding, that they are enabling us to be really efficient in creating modeling tools, and that's because of their reusable generic components that it offers. And we saw the potential for a couple of those components here as well. However, at the same time, once we extracted those components, we didn't really know where to put them, right? So there is not really a place, a common place where we can collect those generic components currently in the Eclipse Foundation so that we can share it with others and also invite others to contribute their components. And that's exactly what we wanted to change with the EMF Cloud project. It's a new incubation project that we have founded initiated a couple of months ago. And the idea is basically to take all this custom code, which looks rad and really hard to manage, and put them into something structured, systematic, generic, and reusable. Basically, we want to enable the adoption of EMF in cloud-based tools with EMF Cloud. So to make it allow to use EMF on the cloud in cloud applications with less effort, to have more standard components, and to have these best practices available and reusable at some place. And that's exactly the goal. Maybe I'll directly mention EMF.Cloud is not here to replace anything in EMF. Maybe some people have thought so. It is definitely not. It's actually quite the opposite. It's trying to make the greatness of EMF available. So it only is adding orthogonal functionality to make it available to be used efficiently in the cloud. So what is EMF Cloud? I mentioned already, it's an Eclipse incubation project, and the goal is really to provide a common home for components that facilitate or simplify in whatever way the usage of EMF and its ecosystem in cloud-based application. The idea is that people the community can contribute components into this project so that they can then incubate inside of this project more and more until they eventually become sort of like a standard component that you will always just use when you, for instance, need to communicate between a client that needs to have some EMF-based data from the server, for instance. And also what's really, I think, one huge benefit in the whole EMF-based ecosystem is that there are clear best practices. So it's kind of clear over the time how to use EMF in your applications. It's sort of encoded in all these generic components. And that's what we also would like to achieve with EMF Cloud, how to do the same thing, what are the best practices, capture them for cloud-based applications. So what is the scope of this project? Obviously, it is as diverse as the modeling ecosystem in Eclipse as well. So we are very, very open to all sorts of contributions, ranging from middleware that make EMF models accessible in a cloud application, for instance, adapters of EMF models so that they are available in cloud-native formats and so on. Editing support for clients that are HTML-based for EMF-based models, as well as also through to tooling for actually creating Ecore models. No worries, come in. And as well as also provide example applications that actually encode these best practices, what I also meant before. So, of course, we were not just going there and say, okay, let's create a project and wait for something to happen. Of course, we also want to start this project by providing actually 3 first contributions. There will be coming more and more in the future, I hope. But the first 3 contributions that we are actually are currently in the process to be adding to EMF.Cloud or have already done it is 3 things, and I will talk about these 3 things in the next couple of slides. So the first one is a coffee IDE, which is a cloud-based modeling tool, and here it's not so important that it's about coffee or some way to manufacture coffee makers or something like that. It's really about providing an example that can be used as a blueprint and that sort of encodes the best practices. Because during developing the applications with our partners, we actually faced quite some challenges, so open questions that need to be addressed and need to be thought about. For instance, like which EMF components can be reused in the server, how to integrate it there, where to put custom specific functionality. Is it more like to put on the client, better to put it on the client side or do it on the server? What is the bandwidth of reuse potentials when we do it this way or the other way, and so up and so forth, how to do the client-server communication, and so on. So, and we have dealt with all these challenges in our projects, and what we would actually now like to do is to provide an example model to also somehow document our opinion on how these different challenges can be addressed. Of course, there might be other opinions or there might be other ideas that are better for other solutions, but this is just a solution that worked for us for a couple of applications and that I would like to share. The idea is that this tool reassembles really a typical modeling tool, so we looked at all the tools that we have been building in the last years and extracted those typical recurring parts. And by that, we allow it to be sort of like a blueprint for developing your custom modeling tool. So you can just get it, look at the code, see how it is done, and try to achieve the same thing. Or if you say, okay, they did it this way, but for my use case, it's better the other way, then that's also just fine. But it's really just to help you getting started with that. And last but not least, it is a great help if you are building generic components that you have a running example. So Just to, I'll be very quick on that, just to give you an impression of how this tool looks like. I will give a demo in a second, but also not too detailed. Like, what is this typical modeling tool? It's basically a tool that is based on Thea that provides different ways, different representations and UIs like forms, diagrams, text, and so on, to interact with an EMF model that lives on the server. And it adds additional components that produce value out of those EMF models in terms of, for instance, that you can run analysis components to compute some metrics or things like that, that you can generate code. You even can then edit this code there and debug it, step through it, and so on. And also these two things should be somehow connectable to projects of the Eclipse modeling ecosystem. Right, so as I said, I will not go into too much detail to have enough time for the other components. There was a talk, unfortunately, yesterday, which went way more into detail about all these aspects of this tool. So if you haven't been there, you can always just catch it on YouTube later. I will just give a very short demo of what it looks like. So let me just start the server here. Okay. It's loading. So now 15 virtual machines are starting in the US. No, it's just all local, no worries. Basically what you have here, as I showed you before, there is like a custom modeling language, which we called Coffee, which is an EMF-based model. And then here we have a form-based and tree-based UI. So basically, you have, as soon as you click on this master tree, you will get all the details in a form-based UI that you can then, of course, edit here. You can also add new elements. So for instance, I can add a dip tray, which shows up then down here. Inside of that, we can, for instance, add another control unit or whatever, and then can assign values. So that's nice. Of course, one thing that is very often or very common is that you can then open, for instance, some other editor in the context of this editor to specify other aspects. For instance, in this case, we chose that you can now open a diagram editor that's implemented based on GLSP. And this just put it next to it. This diagram editor is also representing then a part of this overall model where you can then add some additional nodes. For instance, here, a new task. Let's just call this whatever. And then we can add an edge between that. All right, then it also includes, like I mentioned before, code generation. I won't go into too much detail about that. And then you can also run analysis based on a textual custom modeling language that you can use to configure it and then perform the analysis. It's then running on the server, and then you get some cool visualization of the result of this analysis. All right, so that's basically the first part. So we will be contributing that very soon. We are just waiting until all the dependencies of this tool is already contributed, but you can already check it out now because it's currently also open source, but still on our own GitHub. So you can also look at it now, but it will be soon also in the Eclipse EMF.cloud project. So the next component that I would like to highlight, because that's something that we identified as a requirement more and more when building these applications, is the so-called EMF, or we call it the EMF model server. So you might wonder, why is it actually needed? We can actually perfectly use EMF on the server with or without OSGI. You can use it to load, manipulate, manage models, even proxy resolutions, fragmentation, all that works out of the box. And of course, this is not only true for EMF, but also for your custom EMF-based modeling languages. They would just work, so this model part would just work on the server, right? So why did we still require an additional component? The reason for that is that we very typically in these examples that we have seen before are dealing with different sorts of editors, like form-based, textual, graphical, and so on. And of course, these different editors, they typically represent a specific part of an overall shared model. So there is an overall shared model here somewhere on the server, and this editor only captures this part, and this editor captures, for instance, this part, but there can be, of course, overlaps between those models, and you really want to use both editors at the same time. So how this is actually implemented in like a microservice architecture based on this language server approach is that we have for each of those representation-specific services that run on the server that can then be, for instance, used. So these services on the server will then connect to the EMF model, will load it, and will then provide the information in an optimized way for the respective UI component. So that's all fine, perfect. That's how the language server architecture teaches us to do things. And it's also super flexible and nice. However, when there are overlaps, of course, one change in this editor will very likely affect maybe the state of the other editor, right? Or of the model that is behind the other editor. So when I rename something here that is also shown in this tree, I want to see this change immediately. But the microservice architecture tells us, okay, these three components should actually run in parallel in own processes, be very flexible to be combinable in all ways. But now, of course, we have a requirement to synchronize them. The obvious way is to let them communicate with each other and synchronize like that, but that's of course not a scalable approach at all, right? Because when you have like not 3, but 15 of them, it doesn't work. So what we actually have to do is to sort of create yet another microservice that takes over the synchronization task, and that helps to synchronize the state that all these different services actually require. And that's what the model server is all about. It's not there to be some sophisticated querying mechanism that you can use on the cloud or so. It's just addressing one particular issue, and that's representing the runtime state of loaded models, kind of, if you like to have it, a shared editing domain. It's really an orthogonal microservice that you can use to solve this particular problem. And what you use inside of this model server, whether you use CDO or XMI or XText, doesn't matter. That's up to you. This is really just for synchronizing it. And it does so by providing you sort of a command-based change interface, notification mechanism via sockets. I will show you that in a second. It is a Java-based server, obviously, because we want to reuse EMF, which is Java-based, of course, but it is then providing you with a REST framework it is then providing a REST API as well as socket-based API, and to implement that, we reused quite a popular REST framework, which is called Javelin, so we like that, using that a lot. And it, with that, provides all the clients, and really even if they're running on the server, the clients of the model server provides them with a REST API to create, update, patch, save models, all of the typical operations that you need. And since there will be very diverse microservices connecting to that, we also, to make it easier, we provide multiple formats, so you can request the model either in JSON or in XML, whatever is easier for the client. Last but not least, we also provide a client API. We provide actually two of them. One is optimized for, one is Java-based and one is TypeScript-based or JavaScript-based. So that depending on how your service actually looks like, you can choose which fits best for you. So how does that? Does this service look like? So we have basically first to start this model server in a workspace folder, initialize it with a workspace location. That's important because EMF has also this workspace dependent way of resolving things, so you can do that. And then you can use the client API to, for instance, load something by just connecting to it and then get the model, and then you will be called whenever the service gets back to you. Note that in this model server, if you choose to, the loaded resource will only be reloaded once and will then be shared among all the clients. Of course, there are other methods, but I won't go too much into detail. So next, if you are interested in getting notifications about changes, then you can subscribe and react to those changes. And optionally also even synchronize your own state. So these parts can then synchronize their own states of the model that they're interested in. Therefore, you have this subscribe method where you can then provide a listener, and then you will get, whenever there is an update, you will get basically a message that tells you which command has been executed. There is one default implementation for how these commands are serialized, sort of like a codec, which is JSON-based, but you can also implement your own if you like. So how does it look like? When one service wants to patch a model, it sends, depending on the codec that you selected, it sends a description of the command to the server. The server will receive this command and then can actually apply the patch. If the model server decides, okay, I cannot apply this for some reason, because maybe you were outdated and there is an issue to apply it, they can reject it and let the client know. But if if it is applicable, they will apply it and confirm the execution to the sender. And then in the next step, they will notify all listeners, obviously, by again sending all these, notifying them which command has actually been executed. Note that this command that is then sent doesn't necessarily be one-to-one the same that actually this command sent. That's up to the model server to decide, and that's basically your EMF-based implementation, right? So it can decide of what actually to execute. Finally, they can then, for instance, react to this change and, for instance, synchronize their own state that they have about the model. So let's look at the demo. Just really quick. So actually here, this example already uses the model server, so it's actually already running in the background. If I now switch to Postman, which is a REST API client, I can already, for instance, query all, with this endpoint, query all models that are currently loaded, and I'll get a response here. Okay, the Super Brewer 3000 coffee, that's this one, is actually currently loaded. Cool. So let's, in the next step, actually obtain this, model. So when a client wants to do something with it, so we send a GET request for this URI in the format of XMI, and then we get this information sent from the server. Let's say, okay, we rather prefer to use JSON this time. We hit send. Now we get the same model as a JSON. And just to show you that it's actually the runtime instance at some point. Here I tried to write whatever, but it ended up being whatever. So this is actually the model element that I've added during this modeling session. So we are really connecting to the same loaded runtime instance, because we have not saved this model yet, right? So last but not least, and I hope this works, we can also now patch this model live from this REST client that is at the same time loaded here in this browser. So let's, for instance, send a command where we rename the first automatic task to Holy Cow, for instance. Let's see if that works. So it should be somewhere in here. Let's send. And did it work? Sometimes it doesn't for some reason, so maybe I have to just reload. Oh, yeah, here. That's because basically the tree doesn't immediately update all the time, but anyway, so let's try it again. And now we see here, it has switched to Holy Cow. So we can connect with any client to the same model instance and then synchronize it. Of course, it also works the expected way. So for instance, when I now here select drink and change this to change, then of course we see here that this element is changed and vice versa. So that's how you would usually do it, and not with Postman and the GET request. Right. Finally, I would like to come to the last contribution that we are planning to do for EMF, to kick off EMF.cloud. And that's basically providing an Ecore tooling also for web-based clients, in particular for Thea. And that's because I think creating Ecore models is actually something that has been used in many, many different domains for many, many different use cases. So one is obviously for meta modeling. So when you want to create a meta model and then generate model code, doing the typical EMF Eclipse stuff. But at the same time, many users are interested in using it as a normal data structure modeling language. So that's an additional benefit of that. And it's sort of is just cool to have also a way to allow people to not have to install full Eclipse, to just be able to look at an Ecore model and maybe modify it and send it back. So that's the motivation behind that. We are implementing that based on GLSB, which is a framework for creating diagram-based editors. And of course, we are also using the model server to actually load those models and manage those models so that we can at some point also then have things like a property view that is open next to it in a separate editor and so on. One thing that is, of course, given and, of course, important is that it is 100% compatible, so you should be able to load any Ecore model that has been created with EMF, and of course should be valid XMI. And we actually do so, because that's actually pretty easy to do, because we are just using EMF on the server anyway, so there will be no problem with that, because GLSP on the client doesn't really need to know how to create, for instance, an E-class. It just sends it to the server and it will create the E-class for you and then updates the client again. So, right, with that we maintain all the cool functionalities of Ecore, like code generation, validation will still all work without any issue. So let me just give you a quick demonstration of that. So first of all, I have to kill this other server because they happen to be listening on the same port. Yes. Then I'll start the GLSP language server for Ecore models. Good. And finally, I have to start the Thea backend for that. So please note, this is only like a first implementation that we did. So we started a couple of months ago to really work on that. It's, I would say, a little bit sketchy still, but it's already capable of really opening Ecore models, generating a diagram for it, adding classes, adding attributes. But for instance, you cannot move attributes from one to the other. You can, the styling is not perfect at all. That's not something that we have been focusing so much on yet, but it's still a first version that we then plan to incrementally improve. So without talking about it too much, let's just show it. Whoop, sorry. Here, let's open a browser, localhost. No, that's the wrong workspace. Open, switch workspace. Sorry about that, I thought I had it open before. This one. So in this workspace, I have already opened one Ecore model, which is super easy. It just has one class diagram with references, containment reference, and normal references. We see that we have attributes and stuff like that. And obviously, we can now, for instance, create another E-class. We can give it a name. For instance, let's call this one E-class. And we can then add an attribute to it. And obviously, we can also then add a reference, for instance, to this one. And the cool thing really is, now if I, one second, open the same Ecore editor in the code editor, so those of you who know XMI are now have an advantage, because as soon as I save this diagram, we will immediately see that we got actually 100%, of course, 100% valid Ecore code, XMI code that represents exactly those things that I've just edited here in the diagram, and I, of course, can also then just delete this attribute again, hit again, OK, and then we only have the reference anymore in this class and not the attribute anymore. So that's pretty cool. What else we can now do quite nicely is to use all the cool stuff that also Sprotty allows us to do, like automatic layouting and handling really large diagrams. So just to show off a little bit, we used probably the largest meta model that no one really knows by heart, and that's UML. And we used this Ecore file and just imported it, automatically generate now a diagram for it. So there is no manually created diagram, and just open it. So let me try that. It takes a little bit, but now you see, bam, it's all on position 0, 0 for now. Probably not very useful, but we can now in the next step run a layouting algorithm on that. It's also taking a few seconds. So now the layouting algorithm is done. And I don't go into too much detail because I guess it is a little bit too hard to, to look at it. But that's just that you see it is a sort of scalable technology. We can just wait for 0.7 seconds and then we render such a diagram. And just that to show that we are not lying, It's actually a diagram, and you can really also just remove something now. Tack. Now we have to look it up where this class was that I removed because I touched my scroll wheel. Anyway, you will believe me that it's gone now. Right, that's all for now what I wanted to demo. So coming back to the slides. So in summary, EMF Cloud is really there not to replace anything about EMF. It's really the opposite, to make EMF and all these cool technologies available in cloud applications. It's already has been created. This is the URL of the project at Eclipse. We are currently working very, very hard on creating also a website. So Jonas is already nodding back there behind. It will be there in a few seconds, you said I should say? No, maybe in a few days. So very, very soon. We have already contributed the EMF model server. It's currently in IP review, so it will be there super soon. And we are in the progress of also contributing the other two components that I've just shown. We are just waiting for them. We are waiting with them until the others are accepted and have been already pushed, so that because obviously the Coffee IDE, for instance, has a model server dependency, and we want to have first the dependencies in, obviously. Also, there is more to come, so we are identifying more and more of these generic components that we would like to actually add to EMF.cloud. So we are thinking about having a Thea-based or Thea-native EMF UI, similar to what we have in SWT, so that we get nice trees and so on without a lot of things. And we really hope also to get input from you, what you would like to see in this project and what you maybe have already started implementing for your application-specific projects. And we welcome any sort of contribution, because after all, it's our, and with our I mean the community, this is supposed to be our common home to collect all different technologies and frameworks that facilitate and simplify the use of EMF in the cloud. And with that, please contact me if you have any questions. I'm very grateful for your attendance, and thank you for any questions that you might have now. Thanks. 5 minutes for questions. Yes, please.
So you mentioned that it uses Sprotty. My understanding is that Sprotty has its own, I think it's an S model and a kind of model. So do you do some translation between the EMF model and Sprotty's internal representation?
Very good question. So the question was, we are using Sprotty, or basically GLSB is using Sprotty as a rendering technology. Basically, so everything that you see here inside this box is Sprotty. What is then GLSB on top of it is like that you have a palette, that you have editing tools and stuff like that. That's GLSB specific, but the rendering is Sprotty. And the question was now is, how do we get from this model to this Sprotty specific representation of the graph, which is called S model. And so that's the task of this GLSB component over here in this, I would say, port or connection to the model server or to any other data source, to take this data source, transform it into something that the diagram can render, and then send it to the client, because it's actually super application specific, right? So only you know how you want to have your model rendered in a diagram, and that's the task that is encapsulated in this server.
So what I didn't get is the model server basically serving the LSP server and GSLP server and the JSON forms server. So do these requests models from the model server?
Correct. If you want to do it like that, of course, it's only relevant to do it like that if you have to support synchronous runtime states among those services. If you, for instance, choose to not have it for LSP, you can also implement it otherwise. But we actually used, for instance, Xtext here. And in one proposal provider, we need to propose when the user hits control space in the text editor, we need to suggest, for instance, all the tasks that are listed in the diagram, and to know what the runtime state is and what the currently available tasks are, we obviously need for that to contact the model server and ask it. but they are connecting to that directly, yes. Yes, please. That's correct. So the question was whether it's basically a model registry that provides an API or a REST API to allow clients to get that, and that's exactly what it is. So it is not trying to solve anything that has not been a problem for us yet. It's really just solving the issue of sharing the runtime state. So basically how you set up your e-packages and how you set up your package registry inside here, or whether you use CDO or not, it's all up to you. It's really just the communication and runtime state part. Store, yeah. No, we don't. We actually want to have that orthogonal as an orthogonal aspect to it. So here there is a command protocol, I would say. So when this service wants to change something, it sends a command in a certain codec, as we call it, to the server. But whether the server records that based on EMF store or CDO or whatever, that's actually something that we would like to keep orthogonal to the model server itself. So you can still do it with CDO or EMF store or whatever, but it would just be inside of the implementation, inside of the model server. Ah, okay. You can certainly do that. But in that case, when it's really all running in one process, you can actually use the resource set sort that already helps. Yeah, of course. And you can think of this as a replacement for the resource set that you have when you run into one process, which you don't in this scenario, obviously. So really trying to address this particular issue. But you can have a look at it and see if it's useful for your case as well. I think we have like 30 seconds left. There, one very short question, maybe. Yes, please. Yeah, sure. So actually, it's completely also orthogonal or independent from that. So when you use Xtext here as a language server, you can use it in two ways, actually, Xtext. You can use Xtext to access the model server. That's one thing. That's what we actually did here. And the other way how you could use Xtext is use it as a serialization of your models so that you don't use XMI or something like that, but use an Xtext grammar. And that's what you can just use here. The model server doesn't tell you how you actually load your models, so you can use Xtext perfectly fine there. Great. Then thanks a lot again, and see you soon. Goodbye.